It's a real pleasure to be here, and I have two small introductory comments. One is that all of you as teachers of science, physics, and probably other sciences as well are really, in my view, the heroes of American culture. You know, we're struggling to maintain a sense in our country that science is important. We want to make sure that our young people learn critical thinking, perhaps even scientific thinking. So really, as much as anything, I think for the speakers today, it was a privilege to be able to confer with you and give you a little flavor of what we've been working on. The other introductory so thank you all for being here and for doing what you do. It's honestly, this is the future. It rests in your hands if you're not nervous enough as it is. The other comment I'll make is that the four speakers that have come before me all conveyed a sense of empirical results, experimental data with sound theoretical results, Newton's laws of physics, and so on. And my talk won't be following in the tradition of sound science. Unfortunately, this topic is a challenging one. I will try to do the best I can, but obviously some measure of skepticism on your part is the best approach to what I have to say. Some of what I'll say to introduce is to segue from the past talks. And as you all know, the Earth remains here in 2015 the only site known where biology exists in the universe. It's rather remarkable that here we are with still that ignorance. And of course, there are 200 billion stars, suns, if you will, in the Milky Way galaxy. And as you just heard Dawn describe, we are hunting for microbial life as a community. But of course, we're also hunting for intelligent life in the Milky Way galaxy and perhaps elsewhere in the universe. So that'll be the nature of my talk today, is to give you a sense as to how far we've come with everything you've learned, for example, in the talks today and elsewhere, how far we may be coming toward answering the question of the possibilities of intelligent life just within our 200 billion star Milky Way galaxy. Now, we all have half of our brain filled with wonderful and credible stories from science fiction writers, many of them very thoughtful futurists, and science fiction movies. And what science fiction has taught us is that the Milky Way galaxy is not just teeming with intelligent life, but it's advanced, maybe thousands or millions of years advanced. You need stoplights in the Milky Way galaxy to avoid the Romulans from running into the Klingons. And as much as this sounds a little bit humorous, we really do have half of our brain arguing that there's no way the intelligent life we see here on the Earth could be unique with all of the stars, and indeed if you then include all of the galaxies, how could it ever possibly be that here on the Earth is the only place where there's intelligent life? And even within our galaxy, with its modest number of 200 billion stars, you might argue that surely there's other microbial life that evolved. And that will be some of the nature of my discussion today. This science fiction story is credible, and it actually occupies an odd, fuzzy, ambiguous part of our brain where we essentially believe it's probably right. Now, that's fine, except for one problem. There are some concerns. And I'd like to start my talk off with some concerns about the credibility of this science fiction story that we have in our heads. One of them is, frankly, we don't have any evidence of life elsewhere. And for a galaxy teeming with intelligent life, never mind microbial life, it's a little surprising. I'll give you some reasons why it's surprising. The moon has been visited by us, interesting place. We don't see alien spacecraft left on the moon. We don't see crash debris. We don't see the obelisk from 2001. There are footprints on the moon, but they're all ours. And so you wonder, and with no erosion on the moon, the footprints from alien civilizations that just ventured to take a peek would have left footprints, and yet we don't see them. So Mars has a similar story. Up until a few years ago, I couldn't put this bullet here, but now we have orbiting spacecraft that take meter-level resolution images of the surface of Mars, and still there are no debris sites from past visits by aliens. You can't resolve footprints, but we would see spacecraft that had been left there. And most impressively, we live on a Shangri-La. The advanced civilizations that are populating our galaxy would have certainly detected our Earth, come here, maybe turned the Earth into a vacation spot with alien hotels on the beachfront property with tennis courts and golf courses and so on. And yet, I think many of us would argue that the evidence for advanced alien life here on the Earth is fairly weak. I would add a few more arguments. Every night, night after night, hundreds of professional telescopes all over the world are scouring the night sky doing research, and there hasn't been one clear image of a UFO or a spacecraft by any of those telescopes, despite the enormous surveillance of the night sky. We don't see the gamma rays that would come from the matter-antimatter engines of the Enterprise or the Klingons. People are looking. There were some, possible detections years ago of the gamma ray bursts themselves could have been interpreted that way, the pulsars. But now we realize that there really aren't gamma rays coming from the matter-antimatter engines. Moreover, we humans, NASA, ESA, we're already considering sending probes to Alpha Centauri. It won't be hard with a number of propulsion systems. And if we can imagine sending probes to the nearest stars, certainly an advanced civilization, 1,000 years advanced compared to us, 1,000,000 years advanced compared to us, surely they would be building solar sails and on some regular basis be sending out robotic probes to the nearest stars. Maybe they would reproduce themselves and continue in their travels. Even if they didn't travel corpuscularly, they would send robots, as we surely will within a century, and yet we don't see them. So there's more and more evidence. And I think the most sort of searing, almost painful evidence we have is that we have searched for the radio transmissions of the advanced civilizations for over 50 years. And the silence is deafening. So there is some worry that the science fiction story about our galaxy populated with intelligent life, technological life, might have some problems. And there's a recent idea that has been promoted by several people, Jason Wright especially, showing it's very easy, actually, over the course of millions of years, for advanced civilizations to hop onto neighboring stars or build spacecraft that are self-sustaining and essentially populate the galaxy. A self-respecting advanced civilization with a 10 million year lifetime with technology would be able to fully populate the entire Milky Way. None of these arguments individually are extraordinarily compelling. You could poke holes, but you can see the list is growing of non-detections, which I would say can't be ignored if you have a model of the galaxy that's teeming with intelligent life. Okay. Now, this question question of the silence has been examined by some people, and I'd like to give you some possible reasons I've heard offered as to why intelligent life might not be as common as depicted in science fiction. And there are a handful of very good reasons, I think, and I'd like to describe them briefly. One is, you heard Andrew Howard and Eric Ford prior to Andrew discuss the exoplanets. We're finding Earth-sized planets in large numbers. I'll come back to that in a moment. But we can't measure, as Dawn mentioned, the amount of water on those planets. And one thing we know is that the Earth acquired its water by asteroids and or comets that hit the Earth. Some number of them left some water. We now have a planet that we enjoy that has only a droplet of water, metaphorically 0.06% plus or minus of water by mass in the Earth. And so with that sort of fragile amount of water on the Earth, you might wonder, what about other Earth-sized planets? How much water might they get? And Sean Raymond gave a great talk describing the stochasticity of the delivery of water to Earth-like planets. And I'll expand on his notions. Some Earth-like planets, Earth-sized planets, might receive much less water, in which case some or even all of it will be soaked into the sponge of the interior of the Earth-sized planet, and we would have a dry desert world for such Earth-sized planets. Now you might say, oh, come on, what's the chance that a planet really wouldn't have any water on the surface at all? Well, you just simply look at the two planets on either side of the Earth, Venus and Mars. And there you see 2 for 2 planets without liquid water. For different reasons, one could argue about it, but planets with dry surfaces, Earth-sized planets with dry surfaces, may be quite common. Alternatively, some Earth-sized planets might receive just a couple of drops of water, so much that the depths of the oceans are greater than the height of the continents due to the admixture of water on the one hand and how well plate tectonics is working on the other. And so you would end up with Earth-sized planets, just another droplet, that would be like a bad Kevin Costner film. So it's possible that for every 1,000 Earth-sized planets, only a few of them have both continents and water. Why is that important? Sure, a water world will have no trouble supporting bacteria, fish, maybe even birds. You might even imagine marine mammals if you forget about the fact that they had to go on land and come back. But to develop technology that allows you to build, grand pianos and do fine art and literature and build spacecraft and computers, you probably need dry land. So you need both. And it may be that the Earth is more of a 1 in 1,000 type of Earth-sized planet. Nobody knows. Here's another reason advanced technological life might be more rare than science fiction thought. We humans imagine that we reside at the pinnacle of Darwinian evolution. We're at the top of the food chain. We think we're a logical end product of evolution. But the evolutionary biologists disagree. I've had many discussions with eminent evolutionary biologists. They describe the thousands of ways that species compete for resources, reproduce, survive, and do just fine without being able to play chess. And no better example exists of this fossil record for evolution that does not favor intelligence than the dinosaurs. They not only roamed the Earth for 150 million years, they ruled the Earth for 200 million years or so. And yet, as we learn in second grade, they had brains the size of walnuts. They didn't evolve larger and larger and larger brains. It's a very interesting thought experiment to imagine each dinosaur egg, the smartest of the resulting baby dinosaurs that had a higher than average IQ, didn't outcompete the dumb dinosaurs, apparently. Otherwise, brain size would have increased. So they had brains no larger than those of chickens, and in fact, chickens are the ancestors of dinosaurs. So Evolution doesn't favor intelligence much. I've had experts on dolphins tell me that there's no pressure on dolphins to be even smarter than they are, and the great apes as well. So, as a sort of a joke, you can ask yourself in your daily life, do you see animals that are evolving toward more intelligence? It's kind of cute to think about how the internet has great concert pianists, but in fact, even the mammals on land aren't getting smarter. There's no pressure. And interestingly, there are many species that have no brains at all. And they've never felt any evolutionary pressure to develop even the smallest cerebral cortex.
Some scientists estimate that
see if I can get rid of the sound.
Mass of living things
no, I
ocean.
Can't. So we all know that jellies have no brains. They've been around for hundreds of millions of years. They survive perfectly well and even evolve. Finally, there's another reason intelligent life might be more rare, if I continue my pessimistic sort of bummer part of my talk. And that is and we all know this, once a civilization does develop intelligence and technology that comes with it, those attributes might threaten the long-term survival of such a civilization. And obviously we all think about this here on the Earth. So we don't know what the typical lifetime would be of a technologically astute civilization. We ourselves have had radio technology for a mere 100 years. And in the lifetime of the galaxy of, billions of years, we better survive a lot longer than 100 years. We need thousands or millions of years to have a chance of overlapping other advanced civilizations that have similarly come along. Maybe intelligent civilizations in the galaxy are like lights on a Christmas tree that flicker on and flicker off, and if the duration of being lit is short, then they don't overlap much. Okay, that ends the bummer part of my presentation. But I think we have a special responsibility with the backdrop of science fiction, with the search for intelligent life that I'll describe in a moment, to realize that this is an open scientific question. It's not a matter of when will we find the intelligent species. The question really is, what's the density of advanced civilizations within the universe? What's the average distance between advanced civilizations? Now, there is cause for optimism. And I'll go through what I think are the many reasons to be optimistic. You heard Andrew Howard describe the fact that there are many Earth-sized planets being discovered that are in the so-called habitable zone, where water would be in liquid form if it exists. You also heard him describe the fact that when you build a histogram from the Kepler mission of the size distribution of planets found by Kepler, there's this remarkably wonderful set of planets that are very common, that have sizes nearly that of the Earth. Surely there are plenty of planets, billions, probably tens of billions of planets in our galaxy that are the size of the Earth and even the temperature of the Earth. And if you put all that information together, somebody asked a question a couple of talks ago, how far away, I guess it was during Andrew Howard's talk, how far away from us here on the Earth is likely to be the nearest habitable Earth-sized planet? And you can do a quick calculation to figure it out. Here we are in the suburbs of the Milky Way. If you do the thought experiment and allow your intuition to plug in, you might shrink the Milky Way galaxy down to the size of the United States. And there we are at KITP. And you could then ask, well, if you shrink the galaxy down to the size of the United States, how far do you have to travel in this shrunken galaxy from here at KITP to get to the nearest habitable planet? How far away on this scale? And the answer is across campus. And you can do the math in your head, actually, knowing how common Earth-like planets, or I'd be more careful, Earth-sized at Earth-like temperatures planets are. You really just hop, skip, and jump to the nearest habitable world. As Andrew Howard said in answer to the question, about 12 light years. Okay, so now I'll move a little into dangerous territory here. Most of what I say won't be true, but that's okay. You can sort of decide for yourself how much to take home. And the question I'd like to estimate the answer to is, well, how many advanced technological intelligent civilizations are there in the Milky Way? One number that we know now from the Kepler mission, there's tens of billions of planets the size of the Earth that are at lukewarm temperatures. Surely some of them have the right amount of water, even if it's 1 in 1,000. But if you simply do some simple calculations, there are billions of Earth-sized planets with water on them. And then the question that we have to answer is, what fraction of them develop not only microbial life, but intelligent life? Nobody knows. And so you can take a poll of your students, you can take a poll of your colleagues, and the most pessimistic answer I've ever heard is that if you have an Earth-sized planet in the habitable zone, 1 in a million develops intelligent life. It actually might be worse than that, but let's adopt 1 in a million for the moment. You do the math, you can have your students do the math, 1/1,000,000th of tens of billions, you see there must be thousands of intelligent civilizations. Some of them sprang up thousands or millions of years ago, and so they have iPhones that actually work as phones. Maybe. Yeah, I have some text messages too. Okay, so this now agrees with science fiction. But we know there's a problem, but I'm going to keep going. There is an argument for thousands of advanced civilizations within our galaxy, a la Star Trek and Star Wars. So let's keep going. And now I want to go into a little more detail about the Drake equation, because I think your students can really dig in and enjoy this. Frank is a good friend of mine. We email almost every day. We're working hard on SETI missions that I'll describe in a moment. But with the Drake equation that you heard Dawn describe, one can at least try to estimate the number of civilizations within the galaxy. Let me walk through what Dawn did with a little bit of a twist. Here's the equation again. The number of civilizations in the galaxy is equal to the number of stars in the galaxy times the fraction of them that have habitable planets times the fraction of them on which some type of life, microbial life, say, appears, the fraction of them that evolves via Darwinian evolution or any other process to intelligence. And then there's this rather annoying concern that you have to take into account how long that civilization lasts relative to the lifetime of the star. And that could be a small fraction. And you can have your students estimate values for each of these and try out different values. As you heard Dawn say, we don't know most of the answers. We do know there's 200 billion stars in the Milky Way. We know that roughly 20% of all stars have a Earth-sized planet in the habitable zone. So you can multiply these two numbers together as the first two terms. And then, as Dawn said, we don't know the values of any of the other terms, but you could certainly ask your students to guess in the best of their abilities. And what's interesting, of course, is that when you put in representative numbers, guesses, for these three values, you're fighting against an enormous number, 200 billion stars. So one of these terms is going to have to be tiny, a millionth or so, in order to drive down the number of advanced civilizations to 1. And that's hard to imagine, but it's still possible, and again, an interesting exercise. So, again, in the Milky Way galaxy with its 200 billion stars, 20% have Earth-sized planets in the habitable zone. That gives you the 40 billion Earth-sized planets I just mentioned. But there's another nagging problem, which is we don't know what the term Earth-like means. We don't have a definition for the term Earth-like. What are the properties of the Earth, of the myriad properties? And Andrew Howard mentioned some of those: the presence of the moon, Jupiter, the chemical composition of the Earth, its orbit, circular, and so on. What are the properties of the Earth that make it habitable and therefore Earth-like? And one of the interesting aspects of this question is that we can gain some insight by looking at the least hospitable places on our own planet Earth. And there's no place on Earth less hospitable, I think, than our precious national resource, National Park Yellowstone. And the reason that's thought to be so is that the water comes out boiling. In the winter, there are many feet of frozen water, snow, of course, and the water has a pH of 2. And so you could hardly imagine life forms enjoying such enormous fluctuations from the water boiling to the water freezing, and all the while being acidic. You can go there yourself and have some fun, steal some pH paper out of the chemistry room in your high school, and you go to Yellowstone. Don't tell the park ranger that you're going to test the pH of the hot springs at Yellowstone. You can see I did that, and sure enough, the pH is 2, just like you read in the textbooks. Even the boiling hot springs that are clearly boiling, you toss in your pH paper that you stole from high school. And of course, here with this water, you better attach the pH paper, as I did, to a black metal clip and attach that to a string and toss the whole thing into churning cauldron at Yellowstone. And, the water's dangerous, to say the least. And when you do that, you find out that the black clip is no longer black. The pH comes out 2. You can't quite see the color here. The clip is corroded, and then, as if to laugh in our human faces, you draw up algae happily living its life in that water. They're partying. They couldn't care less about the boiling and the pH thing. They don't know about pH paper. They don't care. And it just shows something that was the theme of Dawn's talk too, that these hideous environments are just lovely. And it gives you a sense of the diversity of Earth-like planets that might be out there. These little critters that thrive are communicating with us, telling us that other Earth-like planets, even if they're alkaline, if there's very little sunlight. Dawn mentioned some photosynthetic processes that thrive without much sunlight. No matter the temperature, acidity, and sunlight, and even sources of food, they do just fine. So there's an amazing message that these little critters have told us about life in the universe. And I really have taken this to heart. I think all of us have. And of course, the message that those people doing this kind of research tell us is that where there's liquid water, there's life. And essentially vice versa. Where you find life, there is liquid water around, even if it's the Antarctic. Okay, putting that information together with the mathematics of Darwinian evolution, you really can't escape the conclusion that, maybe intelligence isn't a primary end product of Darwinian evolution, but surely there will be some environments, not unlike the East African savanna here on the Earth that led to Homo sapiens. There will occasionally be some environments where intelligence pays off, and that those species will give rise to offspring for whom the smartest of them will better reproduce. And then if that's the case, you can imagine intelligent species emerging once you have the microbial life, even if they start in an extreme environment. So with that as the backdrop, one ought to be optimistic about intelligent life in the galaxy. And so we should be searching. And one of the activities that Frank Drake started, and Jill Tarter has been a champion for decades, others of us, Dan Wertheimer as a leader now, are working on, is indeed different ways of actually searching for technology out there in the Milky Way. And I'd like to spend a little bit of time to close my talk describing some very powerful ways with our current technology that we could detect intelligent folks out there. One of them is a newcomer, and I want to start with it, looking for optical light, visible light from advanced civilizations. And the reason this makes sense was first understood by Charlie Towns, who just passed away about a week and a half ago. Charlie wrote a paper in 1961, here he is with Schwartz, describing communication by optical masers. And if you read that paper, there are great quotes. A civilization out there could be 1,000 years ahead of us, Towns said. It seems possible that some being on a planet orbiting a nearby star could send a bright enough beam that we could see it, we could detect it. And sure enough, after his discovery and invention of the laser, nowadays we all know there's a lot of laser communication occurring here on the Earth, especially ground to satellite and satellite to satellite. It's being used commercially. It's being used for the by militaries all over the world, and there are good reasons. Lasers offer many advantages over, say, radio wave communication. Shorter wavelengths gives you higher bandwidth. Laser beams are less divergent. The beams are sharp, so you can maintain privacy. You don't need much power to carry gigabits or terabits per second. So there are lots of good reasons that indeed the public and private communities are moving toward lasers. And interesting, even the astronomical community, we now equip our telescopes with lasers that make artificial guide stars that we use to correct for the turbulence in the Earth's atmosphere. And when you put all this together, you realize that there may well be advanced civilizations out there in the galaxy who similarly are using. And indeed, how would they communicate with their spacecraft? Right? You send you're an advanced civilization, you send spacecraft by the thousands all around. You can't string Ethernet out to them. You can't string fiber optics. You can't string copper. You have to use lasers. So it might be that our galaxy has laser beams shooting through it from one civilization to a spacecraft or to another planet, or to one planet to another planet. The galaxy could be lousy with laser beams, sort of like a mystery movie in the in the museum where they have the security system and the laser beams are pointing in all directions, and James Bond has to somehow tiptoe around the laser beams. And some of those laser beams, inadvertently or maybe even purposely, might be aimed at us. In which case we simply open our telescope domes and look for the lasers. You have to do so. It would have to be a special project, and I'll describe one to do that. There may well be a galactic laser internet, and we humans just haven't tapped into the internet yet.
But I'm curious, could you distinguish the galactic laser internet from just Starlink?
Yeah, so the question is, could you distinguish the galactic laser internet from starlight or other sources of light? I'll describe that right now. So we are using, a group of us are using the Keck telescope in Hawaii. You might know the Keck telescope. It's located on Mauna Kea, a hopefully dormant volcano on Hawaii. And we use the giant spectrometer, high res, to spread the light out from stars into all of their wavelengths of light, blue, green, yellow, red, even the near infrared and the ultraviolet. We, in fact, among other stars, nearby stars, we also survey Kepler stars. We're surveying about 1,500. You see them here. Some are Earth-sized, some are super-Earth, some are Neptunes, some are giants. And here they all are that we're surveying. And what we do is we zoom in and have the entrance slit of our spectrometer at the back of the Keck telescope zoom in on one star, and we take a spectrum, spread the light out into all of its wavelengths, and we're looking for just one thing. One specific wavelength at which there's a bunch of light, a lot of light compared to the rest of the star, thereby distinguishing it from the star. And I'll show you some of our actual data. This is a little complicated, but just bear with me. Here's a zoom in. These white lines represent how much light at different wavelengths from left to right. There's a night sky line. The sky glows. And so the whole length of our entrance slit is lit up at that specific wavelength. That's not a laser, right? Because the lasers from the advanced civilizations are, light years away. We wouldn't resolve them. We wouldn't see their extent, whereas this thing obviously has linear extent. So we see the night skylines, we see the stars spectrum, distinguish those. We can even distinguish the emission lines from quasars, from planetary nebulae, from H2 regions, other sources of emission. And then here's what a laser would look like. If you zoom in on a little patch, if there were a laser in the Milky Way galaxy pointed at us, at Earth, we'd see a dot. It's a dot. It's a little complicated, but the idea is it's just one wavelength. Just right. This is increasing wavelength from left to right. So this is just one wavelength, and it's unresolved spatially. It's a laser emitter, a machine out there light years away that wouldn't have any extent angularly in the spatial direction, less than 1 arcsecond of an angle. So we have very good ways of calibrating what those dots have to look like to truly be extraterrestrial lasers. And we've been searching now for a couple of years. We haven't found any yet, but we're just about to launch a new search of about 2,000 stars. So I just wanted to let you know that there is a very exciting way, and other people are doing this as well, in the infrared, in the ultraviolet, looking for lasers from the galactic internet, if any. And then, of course, as all of you know, method number 2 is to simply search for radio waves, as Frank Drake started to do back in the early 1960s. And somewhat ironically, the Green Bank Radio Telescope facility in West Virginia, where Frank did his earliest work, is still available, albeit with a refurbished new radio telescope, and obviously a very important way to continue doing SETI searches, SETI, the search for extraterrestrial intelligence, is to use the world's largest radio telescopes. Green Bank, to this day, is the world's largest steerable dish. There is no larger steerable radio telescope in the world. And so it's a viable place to do SETI work, except for one interesting problem. NSF has started to run out of money, and they've told the world that by the end of 2016, i.e. a year from now, they will have to shut down this marvelous radio telescope in West Virginia. And they're soliciting partners, frankly. And the cost, if you want to buy half of the time, day and night, on the Green Bank telescope, $4 million a year, and you got it. So we're actually working hard to try to help NSF to find this money. And SETI, the search for intelligent life, might be a way to attract private funding. But so far we haven't been successful. One of the fun tricks is that, as you heard many of the speakers say, we now know of multi-planet systems, stars that have 2, 3, 4, 5, 6, 7 planets, and we know where they are in their orbits. So we can wait until the planets line up. When planets happen to line up with our Earth, if they're communicating with each other, we might be able to eavesdrop on their interplanetary communication. And we are doing this. Andrew Simeon, a postdoc at Berkeley, is doing exactly this, indeed using the Green Bank telescope. Waiting until planets line up, and then pointing the Green Bank telescope at that Kepler star with the lined up planets. So there are tricks like this that we can do now that we know where the Earth-like planets are. And I'll finish with one last slide that has just come to my attention, and just literally in the last couple of weeks. There's a new international effort to build an even larger radio telescope. It's called the Square Kilometer Array. Some of you may have heard of it. It won't be built for another 10 or 20 years, but there's a precursor called Meerkat. And Meerkat is located in South Africa. When it is fleshed out with, I think it's about 64 dishes. I've forgotten exactly how many, each one 12 meters across. Some of them are already built. It will be by far the most sensitive SETI searching radio telescope, if you will, and allow us to pick up the faint radio and television transmissions from civilizations, light tens of light years, hundreds of light years away. So we will, Andrew Simeon and others are beginning to explore the possibility of garnering some of the Meerkat radio telescope time specifically to search for the advanced civilizations that might be broadcasting. So I'll finish and say that it's a marvelous, almost tear-jerkingly marvelous time to find the Earth-sized planets with Kepler, to note that they're common even in the habitable zone. And I think I agree with the past speakers today that offered optimism about microscopic life probably being extraordinarily common. It's just hard to argue against the sequential biochemistry that leads to replicating molecules and maybe photosynthesis. And then the open question, I think, remains about intelligent life. Are there a dozen intelligent civilizations in our galaxy? Or is there 100? There's probably not tens of thousands, because they would have visited. But it's possible that our galaxy has a few dozen advanced civilizations. And to be honest, it's possible we are the only advanced civilization in our galaxy. That can't be ruled out. And one of the interesting aspects here is that whether or not the galaxy is populated has interesting implications either way. If we have kindred spirits out there, how lovely to be able to communicate with them someday. If somehow there is not intelligent life in the galaxy, it means that we humans bear some enormous galactic responsibility to take care of our planet and to take care of our species. So I'll stop there.
Thank you. Oh, questions already.
One of the last statements you made was we would have been visited already. How would they know we're here? Would they be looking at our stray radio transmissions or television?
Yeah, so the question is, how would they know we're here, and would they visit as a result, and so on. As all of you know, I didn't say it, but we have been transmitting almost isotropically radio and television broadcasts since the 1930s. And so there's a sphere expanding around the Earth, moving and expanding at the speed of light that contains the radio and television transmissions, now going out 80 light years. So there are thousands of stars around our sun and our solar system, thousands of stars that, if they have radio telescopes, could simply, pick up I Love Lucy or Gilligan's Island, and they would immediately conclude that there's no intelligent life here on the Earth.
Hi. How far away from Earth would those signals even be intelligible from background noise?
Yeah, so it's a good question, and I'm not an expert. What the experts tell me is that if they point their radio telescopes toward the Earth, if their beam size is a nominal small beam, that helps exclude the background noise. And presumably their radio telescopes are like, the square kilometer array, but times 10. And so they can easily pick up our signals. They may be listening in on this conference right now.
Additional questions?
I have a question with a preamble. So when I was a student in Cambridge, Mass., I saw a poster saying debate between Paul Horowitz and Ernst Mayr.
Yeah.
Kind of dates me because
Ernst Mayr is an evolutionary biologist.
Was, yes.
Yes, right.
So I went to the debate. It was very interesting. Mayr was very dismissive of Horowitz. Horowitz did his best, but I'd say Mayr won the debate. Mayr argued that the problem, well, he said a lot of things, some of which I don't agree with, like Horowitz was wasting his time, wasting his graduate students' time, the university shouldn't support him in his work on SETI and so on. But I don't agree with any of that. But Mayr said some interesting things about intelligence. He said our notion of intelligence, the very word, is so human-centric that it doesn't have any meaning when applied to other species. And he criticized Horowitz's point of view as being non-biological, not understanding the biological sciences or modern evolutionary theory. And he gave the example of elephant earwax, and actually looked on the web recently to see if this exists, any record of this, and I can't find anything about this, but Meyer said, imagine that elephants were in charge, and they judged all other species based on their earwax, because elephants have spectacular earwax, apparently, much better than ours, and so all other species would pale in comparison to the elephants in the earwax index. And he said that's like intelligence. That's humans look around because we have this particular adaptation, and we judge every other species based on this one index. It would be like elephants looking around, looking for elephant earwax on other planets, and not finding it and being really puzzled about it. So I wondered if you had any thoughts about maybe the fact you're getting two different answers when you approach the problem two different ways means that the problem is not well posed or not posed correctly. There's something we're missing.
Well, my response to that would be you've offered a perspective very similar to the one slide and the discussion about the dinosaurs. There is, as I mentioned, a wide variety of evolutionary biology results, also paleontological results that show the fossil record of hundreds and hundreds of species that never got smarter. Very few of them did. And the reason is just what you said, that there are hundreds or thousands of attributes of a species that allow it to compete and reproduce. The cheetahs think that fast running speed is the only way to go. The cockroaches are sure that the hard shell is just what you need. Giraffes would say the same about long necks. And we humans, not surprisingly, think that big brains puts us at the top of the evolutionary tree. And the reality is we're on a twig of the evolutionary tree. So, that does beg the question, is intelligence something that, would normally spring up, or did something happen on the East African savanna 2 to 3 million years ago when the Australopithecine were still sort of climbing around on trees? How rare is it that you get the confluence of environmental factors that forces intelligence to be so preferred? And I don't think any evolutionary biologist has the answer, but I agree with the Ernst Mayr perspective that I've been taught from others like him, that there are just so many attributes, and intelligence is just one. Yeah.
Well, yours, again, based on what we've just been talking about, you're expecting intelligence to have developed a laser, to develop other things, and maybe they make themselves invisible. I don't know, but...
Yeah, so that's a very good point, and it's actually related to something we discussed earlier. It is possible that truly advanced civilizations develop a modest, if not sort of cynical view of science and technology, that they realize that Game Boys and video games and so on are not really the greatest thing ever, and they move more toward poetry and music and interpersonal relations and beauty and aesthetics in general, and that's how they live out their lives, in which case they aren't interested in space travel or lasers or even perhaps advanced technologies of much sort at all. And indeed, you could argue that since technology poses a threat to our own survival, those civilizations that limit, with all due respect to a room filled with science teachers and scientists, it may be that those civilizations that learn to limit their dependence or their interest in science and technology, are the ones that survive the best.
So I'm not sure if previous speakers are supposed to butt in, but I will for a second. And I'll say this only because you mentioned the graduate students of Paul Horowitz. I actually happen to be a graduate student of Paul Horowitz's back in the day. So I wasn't present for this debate with Ernst Mayr, but I can reproduce a little bit of it. And the essence of the debate boiled down to Ernst saying, if you look at the history of life on the Earth, there was something like 1 billion civilizations. A billion species. The Earth was 1 for 1 billion. The odds are astronomically against intelligence. Paul's response is, no, the Earth was 1 for 1. You only have to get it once.
And the other perspective is we were 0 for 1 billion. And the reason you have to, in my opinion, discount humanity is that any advanced civilization like us that was smart enough to ask the question is always going to get 1. So even if the true answer is 1 in a trillion, there's always going to be that 1. So there's a bias by virtue of the fact that we have to exist to ask the question. And I would argue that we should discount that 1.
Well, the first one always erroneously makes that claim.
Right.
So I was curious on something a little bit more technical, but with the laser search, obviously for the accidental pickups, you're counting on some level of dispersal of the signal, and so I'm wondering what the kind of the geometry on that works out to be. What's the optimal distance for a civilization communicating that way to be far away?
Yeah. So I guess you could all hear the question. There's a serious problem with the laser search, which is simply that laser beams are so narrow, they occupy such a small solid angle, a small cone, that the galaxy would have to be filled with trillions of these things in order for the filling factor, a Swiss cheese kind of model, in order for it to be filled with laser emission. Laser beams are just so narrow. You might argue that laser beams are so narrow that there would have to be trillions of civilizations or trillions of laser beams anyway. Otherwise, we'll never see any. So the geometry of the problem, in terms of the narrowness of laser beams and the enormity of the galaxy, makes this a tricky bet.
So I guess maybe a follow-up: has anybody thought about processing all the various planet-hunting signals, thinking that maybe the solution that other civilizations came up with was kind of some sort of Morse code approach to manipulating light with shades or something like that coming off the stars?
You mean like the star shade idea?
Yeah.
Are you thinking? Yeah. Well, I don't know what to say other than when the day comes that we have a star shade or some other means like a coronagraph to block the starlight and take pictures of Earth-sized planets in their habitable zones, a very reasonable thing to do will be to look for laser beams coming directly from them, look for radio waves, look for other sources of some Morse code-like signals at whatever wavelength.
So actually, what's really interesting is we've been receiving the messages for many years, but we don't have the technology yet to receive it. It's on a stream of neutrinos.
Right.
So, I mean, what would hold them back from that? I mean, wouldn't that be a better way, a better mechanism to transmit them? They go through planets and... Right.
And going back in time, if we were doing SETI 100 years ago, we'd be looking for smoke signals. So, there's a very serious problem, which is, in each few decade interval of time, you're going to search for intelligent signals that are just like the cutting edge of what you happen to have in that era. And they've blown by us. They're using tachyons, as you say, and so on. So who knows?
So I think we've reached the end of our time. Is that right, Greg?
1 minute or something or maybe we're well over. I don't know. But
Scott Tremaine has a question.
Oh yeah, hold on.
This scares me too.
This is just a comment. I don't think, Geoff, you're being speculative enough. As most of you know, most of the material in the universe is not ordinary electrons, protons, and neutrons. It's dark matter, and it's quite possible that the chemistry in physics in the dark sector is just as complicated as in our sector. And so it's quite possible that the intelligent life that we're looking for is there, but it's hiding in the dark sector. If that's true, the only way that it can communicate with us is gravitational waves. And fortunately, we are building gravitational wave detectors. They're not designed for SETI, but it's always possible that the first thing we're going to see in a gravitational wave detector is a signal from intelligent life in the dark sector.
I have one more comment. I noticed you didn't mention Fermi in your talk.
It was, so I'll comment. There's a very well-known statement by Enrico Fermi, often deemed the Fermi paradox. I don't think that's quite the right term for it, which is effectively what I was saying implicit in the lack of detections, that long list of our failure to detect advanced civilizations is part of what Enrico Fermi was saying when he said they would have been here if the galaxy were teeming with intelligent life.
What I think is interesting about that is apparently Fermi said that in the 1940s in the cafeteria at Los Alamos, and it indicates he had already a version of the Drake equation in his mind and had already estimated the probabilities, and he just never wrote it all down. It was all in his head, but he formulated it basically as we would today, as you did in your talk.
That's right.
Okay, so I think we are out of time for real now, and so I think it would be worthwhile to give all of the speakers another thank you for their effort.
And may I say we should also give all of the attendees a round of applause.
Thank you for attending. We really appreciate your taking the time and traveling long distances in many cases to come and attend this. So enjoy your evening.